when they would meet, burning moon, they would create offspring. And they would basically have these sparks flying around the moon, and overnight they would create more and more and more offspring, and this whole moon would become pulsating with light. And then gradually, as the night progressed, slowly they would fade out and they would die. And around midnight, so after 6 hours, they would slowly go quiet. So this was not this was programmed in code, but there was no video footage of this. So different from the other show, this is a non-linear spectacle that you could only see if you were one of the tens of thousands windows that were looking down on Victoria Park. So here you see it at one of the heights where there's hundreds of sparks like fireflies flying inside the structure. Very dynamic. Here you also get a sense of scale of the crowd. We had to triple the waiting line because it became so popular. We had over 400,000 visitors in 6 days, which is 3 times as much as a Serpentine Pavilion gets in London.
Oh yeah!
So that was good. But now it's gone. It only exists in people's cell phones. And I have to thank Lee Key for their amazing sponsorship of this project. But it wasn't over. 1 year later, all of a sudden, a friend of mine sends me this photo from Changsha, where in the middle of the highway for Mid-Autumn Festival, somebody was creating an inflatable version of our golden moon. I don't know who did it. I don't know how many of them there were made. I never saw it myself, but I think it's brilliant because it's much easier to make an inflatable version, but it's clearly a copy because it doesn't make sense to make a flaming fireball for Mid-Autumn Festival unless you're a perverted foreigner trying to do something funny. Anyway. More problematic though, was that around the same time I get a phone call from another friend like, hey Christoph, you're building your moon again this year, that's cool. No, we're not building our moon again, what are you talking about? No, they're building it in Victoria Park. I said, really? So I go and check it out, and this is our steel structure, that's what they're building over there. So they had done another competition, and these guys called Daydreamers won that competition. And they won it because it was about recycling, and they were using recycled plastic bottles as a cladding for the moon. But they didn't manage to figure out their geometry, so supposedly, and I don't know if this is true, but supposedly the client handed over our tender documents to them to just rebuild the whole steel structure and clad it, which is not very environmentally friendly because they basically tore down our steel structure the year before. But add to that they didn't find out a clever way to span these big triangles, so they doubled the amount of steel by adding another triangle inside each and every one of them. But it's about recycling, so everybody was happy, except for me. Anyway, that was the Mid-Autumn Festival. Remember this music song? This was a year and a half ago. I was at home with my wife checking out old, going down memory lane. This is Yanni live at the Acropolis in 1993. The song that was supposed to be Chinese was stolen from Greece in 1993. Anyway, that was a golden moon. It was a fun experience. The biggest project I want to talk to you about is the ZCB Bamboo Pavilion, which we did 2 years ago now. And this is done for the Construction Industry Council, which is the Hong Kong government body that's in charge of all the training, amongst many other things, training all the craftsmen in Hong Kong. And they wanted to work with bamboo. And they wanted to use the site that they had in front of the Zero Carbon building to host public events, showcase bamboo's potential and talk about sustainability. And so bamboo is this absolutely amazing material. I'm not per se into it, but I got quite obsessed with it as part of this project. There's 1,200 species, 750 in Asia, and this video shows you why it's so stunning as a material.
The deluge waits another forest inhabitant. This one is particularly astounding in its vigor. It can grow up to 1 meter a day, fast overtaking the other plants around it. The taller it grows, the faster its growth rate, so that in a matter of days it towers above the undergrowth and continues reaching for the sky. Not bad for what is essentially a crevice. It's bamboo.
So this is an amazing species. 1 meter per day. That means that if you're sitting next to it to have your lunch, that by the time you're finished with your lunch, it's this much tall. So it's a stunning plant. It's very different from wood in that it first grows to full height and then densifies inwards. So it doesn't build up its year rings and gradually becomes thicker. It actually densifies inwards. Why it's really important is because it is growing in all the parts of the world that are urbanizing the fastest, where the most construction is taking place. So if we would be able to use that in a different way, we could really lower the carbon footprint of our urban developments. It's been part of vernacular construction for centuries, whether you're going to Indonesia to the Toraja house, which is a tomb which is made from bamboo, or any other parts, you'll find it in vernacular construction going back thousands of years probably. But nowadays it's not part of modern materials because it hasn't gone through the rigorous policy making and building coding as, for example, wood has, which is a material that was available in the UK and the West. So now it's used a little bit more for its maybe symbolical purposes sometimes, or as replacement for steel and wood, but very rarely is it really used for its properties, which are, it's extremely strong, but it is extremely flexible. You've probably all seen Crouching Tiger, Hidden Dragon, where they're kind of flying through these bending poles, and that is because of the cellular buildup of the bamboo. It constantly has these reinforcement rings in there that keep it from buckling. So we wanted to do something that was working with its bending properties. Now I mentioned to you that in Hong Kong there is this scaffolding craft. So all the scaffolding in Hong Kong is made from bamboo. Even the 400-meter skyscrapers, bamboo scaffolding. And the way that works, they don't read plans or sections, but they use body measurements like shoulder heights or the length of a person's leg to define the grid dimensions of their structures. And then they use rules of thumb to define where they need to have diagonals. And they always use a few knots on how to tie them together, that I can teach you in a pretty short amount of time. So it's a very flexible setup. For me, it's almost impossible to climb through it because my shoulders are just 15 centimeters too high. But for them, it's extremely useful to navigate through. And here you see some of the shots of it being used all around Hong Kong for everything. In addition to temporary structures in construction, they also use it for Cantonese opera. So every year, around 40 structures or more similar to these are built by local communities where they all chip in to get these craftsmen to build a structure for Cantonese opera for their local deities. These are all single-story structures made with recyclable bamboo, covered with these thin sheets, and they can host up to 1,500 people, even the bigger ones. So here you see a very rigid typology with a certain modularity that they can respond to different site and contexts with. And it's always the same grid system, slightly changed, slightly adapted. So very flexible, but within its typology rather strict. I've been looking for experimentation with bamboo, and one of the few that I could find was this in 1962, where they did this nice high-par surface with bamboo. And here you see that they're still using bamboo skin rather than the plastic fibers to use connections. But since then, I haven't seen too much experimentation with it. A few years ago, when one of the more famous local architects was asked to build the biggest bamboo theater ever, the only thing that really managed to be done was scale up the structure. So this is the West Kowloon Bamboo Theater in 2013, which is huge. But you can see that it was built to a scale where what determined the size was a limitation of the material. And you already start to see that some of the bamboo is being replaced by fir tree trunks. So we wanted to play around with that, and this is our structure compared to one of the biggest ones. We wanted to see if with computation and equilibrium surfaces and spring particle physics simulation engines, etc., if we could come up with a new typology radically different from what was there before, but using the same materials, using the same knots, using the same techniques and the same people to build it. So this builds up on a big legacy of work that goes back all the way to the late Fry Otto, who I hope you know, Pritzker Prize winner in 2015, and one of the pioneering engineers in complex architecture engineering. So he built the Mannheim Multihalle together with OV Aragon partners back in '74, which is the largest free largest spanning bending active grid shell structure, which you can see here is several halls. And the way this one is built is basically by making a flat grid and then popping it up. Back then, they didn't have computational techniques to help them with that. So they used these physical models where they had a steel mesh, basically, with equilateral edges suspended using gravity to figure out what geometries they could approximate to make these structures. So you can imagine how labor-intensive and time-consuming it must have been to make these physics simulation engines in analog ways. Here you have another closer view of it. Very difficult to make these models. But then this exact data was translated onto site in a larger scale, where they would make these flat grids, and then those were popped up from underneath into the shape that you see there, pulled in at the edges. Diagonals were added for reinforcement. So here you see the popping up happening with these spreaders, where they gradually just jig up the whole structure until at the end they can just remove them. So before and after. Until this again the flat bed structure, until they can basically pop them into shape, and having the bending properties of the wood provide the structural strength. Then they're using the UV directionality of these surfaces to put the skin on top of it, and that's the final at the point when the supports are removed. So this is in the 70s. This is a photo I took a year and a half ago when I was there. So it's still in pretty good shape. It needs a renovation, but it's a beautiful, beautiful structure. Very peculiar, and the only one of that scale that has ever been built. Slowly falling apart a little bit where they're reinforcing the edges. They just need a good makeover to make it work again, with a very nice shape. So this is Friotto and his friends doing experiments with bending active structures in the 60s and 70s. After that one, there was a huge blank period of decades where nobody ever used it because it was just, I assume, so bloody painful to design and do these things. Until in 2000, all of a sudden, Shigeru Ban, together with Friotto, made this, which is the Japanese pavilion in the Expo 2000, which is a similar structure made from bent paper tubes. Again, using physical models, but computation already as well, to make this big structure from bent paper tubes. And since then, all of a sudden, it became on vogue again to work with bending active structures. And the reason why that is, that suddenly people work with it again, is this, that we have digital simulation tools that allow us to know exactly, we can dictate lines to straighten out, or we can simulate what it means to bend one line, or we can simulate what it means to bend networks of lines. So this is just done with grasshopper and kangaroo in Rhino. So with these tools, we decided to give a stab at bamboo architecture. So the way we realized this one is through a very rigorous iterative cycle of digital and physical model making and prototyping. So these are all the models that we made before we went into construction. And the construction itself was basically just the next step in a series of models. So our build project was a prototype in and of itself. We started off with a design workshop with students. I directed 4 teams to try out different ideas. Again, in an iterative cycle, using bamboo, making models like this big, 1 to 20 scale. And here you see the 5 steps that this team went through to arrive at that shape. Starting off from a stable triangle, but knowing that there's a weak point there. Then avoiding that weak point altogether by putting it onto a line, seeing a weakness there, turning it into a grid to make it stronger, still finding a wobbly weakness there, folding the surface onto itself to arrive at a very stable structure from an extremely weak material. Then me and my team, we took this in and turned it into a digital version. So the first thing we did is we took the construction site, we identified the location where we're going to have the foundations, we created a triangulated grid, and then again through trial and error figured out what the exact configuration was that we needed to set up the spring particle force system that allowed us to fold this 3-legged structure onto itself without drawing any of these coordinates, but allowing all of these coordinates to emerge and find their own shape using principles that are very similar to the physical material that we use to make a physical model with. After we did that, we tried to build a first prototype again from that, and it became a huge failure. Material was breaking in areas where we didn't think it was going to. The installation sequence became very, very difficult to find out because, as you see, they're pretty close to each other, and you can bend the bamboo stick easily, but you cannot really weave it when it's getting that thickness. So we had to figure out the hard way how to assemble this, but we arrived at a structure that started to get the whole gist of it. And then in the next digital iteration, we upgraded our digital model to embed all these peculiarities that we found, and here we derived the installation sequence that we thought would allow us to first make a stable structure made of arches, always by only adding members from the top, and then later on weaving in the tension members on the bottom, again knowing that we would never be able to put sticks in from the bottom itself. We always had to lay it from the top. Then with that, we made this 1:4 scale prototype on the roof of our school. So that's CHK. The people with yellow hats are from the scaffolding school, the bamboo scaffolding students. So this structure was made not with bamboo, but with rattan. And rattan is also a grass-like reed, but it's solid. It's not hollow. And because of that, it's a little bit more flexible. And you see how it's slowly drooping the whole time. And we wanted to use this model to check where it would be structurally strong, where it would be really working as a grid shell structure.